Hey everyone, welcome to EX370 Discussion 3. So today what we're going to talk about is Project 1, specifically the multiplication part of Project 1. We're also going to discuss some C to ARM translations and bit manipulation. So I'm sure you're all familiar with multiplying in decimal. So when we multiply in decimal, we multiply by shifting each number as we go. So first we multiply by 6. So we do 104 times 6, and we get 624. Next what we do is we multiply 104 by 2, but we shift it to the left by 1 because 2 is in the tens place. And note that shifting it to the left in decimal is simply just multiplying by 2, and we get the number 2080. Next we just add these two numbers up, and we get the result of 104 times 26. Now, thinking about multiplying in decimal, we can actually apply a very similar set of steps to multiplying in binary. So, the way we're going to multiply in binary is first we go bit by bit. So, we have this number 1011 right here, and we look at the first bit in the ones place. So, in the ones place, the bit is a 1. So that means we can just we do 1 times 1001, and we just add that number. The next bit in the twos place is 1, so we do 1 times 1001, and we also multiply it by 2 because it's shifted to the left once. So that's how we get the number 10010. Next, for this bit right here, it's a 0, so we do 0 times 1001, and we also multiply it by 4 because 0 is in the 4's place. However, since we multiply by 0, it doesn't really matter, and we just get the number 0. Finally, we multiply by 1 times 1000, and it's in the 8's place, so we multiply it by 8, and that's just equivalent to this number. And then once we have all those different computations made, we can simply sum them up. So, since we always multiply by either a 1 or a 0, how can we perform the operation? Because in LC2K, you don't have access to a multiplication opcode. So the way we go about doing that is, instead of just multiplying by 1, maybe we could just add it to itself, or just add the number already to our running total. And then how can we perform the shifting needed by our algorithm? Because again, LC2K doesn't have a shifting opcode. And the way we can kind of shift is, I kind of alluded to it here, is you can multiply by a power of 2. And when you multiply by a power of 2, that's the same thing as adding it to itself. And how can we ensure that we are only multiplying by one digit? So we can ensure that we're only multiplying by one digit. As you can see, we multiply by 1 and 1 only. We didn't multiply by 1 and then 1 times 1001. We can ensure that we're multiplying by only one digit by using a mask, kind of like you did in Project 1A. So now we have some key hints about writing an LC2K assembly. So probably one of the most important things about writing an assembly is adding comments. This makes it easier for you to revisit code because you don't have to kind of think about the past steps you made. You can just say like, oh, this is the code that does this operation for me. And it also makes it easier for us to help you in office hours. Also, make sure you remember how addition, bit shifting, and multiplication all relate. We see that we have 3 statements down here: x plus x, 2 times x, and x shifted to the left by 1. These are all the same. They will all result in the same operation. And also recall that in LC2K, you only have access to the NOR opcode. But for making a mask like you did in Project 1A, in C, you had access to the binary and operator. So, the important thing to note is that you can build any gate in any logical operation from a NOR. So, that's a pretty big hint for the project. Next, we're going to cover C to ARM and accessing memory. So, first we have this memory access in C, and we're going to want to see what that C code would look like in ARM. So, memory accesses are pretty complex and require multiple steps. The first step is to figure out the relative offset. So, since we have an array, the first step we want to do is figure out the relative offset from the beginning of that array. So the way we figure out that relative offset from the beginning of the array is we know that in this line right here, we want to access the bth element of the array. And our array has elements that are of size 64t, which means that in total it has 128 bits. And to get the number of bytes that is, we just divide by 8. So it's equal to 16 bytes. So now, since we know that ARM LGV8 is byte addressable, that means we compute the bth elements knowing that each element is 16 bytes long. So we just do b times 16. However, the one thing to note is that LGV8 doesn't have a multiplication opcode. LGV8 is a reduced instruction set architecture. So instead of including a complex multiplication instruction, instead they just give you access to a left shift operator, and any multiplications have to be handled by a combination of multiple opcodes. So we can easily just compute this number by using a left shift. We can just do a left shift of 4. So what is our first command in LGV8 going to look like? Well, we know that we want to compute b times 16. So that means b is stored in register x1. So we do a logical left shift, and we can just store it in whatever register we want. I'll store it in register 10. So this stores b times 16 in register 10. And the reason why we use a left shift of 4 is because 2 to the 4 is equal to 16. Next, what we're going to do is we're going to figure out, now that we have the relative offset from the beginning of the array, we're going to find the actual offset in memory. The way we do this is we know that the address of the array is stored in x0. So what we can do is we can add together x10 and x0. And we can just store that in a new register. I'll pick register 11. So that means register 11 has the actual memory address we want to access. So I'm just going to erase this so we can get to the next step. And remember that we stored the memory address of array B in x11. Now we're going to use, since we know that each int 64t is 64 bits long, and we know each register is 64 bits long, we're going to want to use the load register command. So LDUR. And what we're going to load is we're going to load register x4 because that's the one associated with n. We're also going to pick which memory address we want to load from. So as we know, we stored the address of array B in x11. So we're going to load from there, but we want to access array b.real. We note that each element in our array is actually 16 bytes long, but each integer of 64 bits is only 8 bytes long. So how do we get the bits 0 to 8? So that's pretty simple. We just use an immediate value of 0 that we offset our x11 by. And this will load register 4 with the value of array b.real. Next, we see that we have the b++. So what we're going to do is we're going to use the add I instruction to increment b. We note that b is in x1, so we just do add I x1, x1 with the immediate 1. Now what I'm going to do is I'm going to pause the video for a few minutes and try to work through the second line. The second line is a little more difficult because you have to figure out how to access bits 0 through 7. You're going to have to access bits 8 through 15 of array b.imaginary. So the process is going to be pretty similar, but you're going to have to think about what offset you use in your load register function, because you want the upper 16 bits of the array value, not the lower, or the upper 8 bits of the array value, not the lower 8 bits like we wanted before. Okay, so now that it's been a few minutes, I hope you've made your way through the practice problem. So just to review, we have the left shifts, we use the left shift to compute b times 16. We then add the offset from the beginning. We then add the relative offset of b times 16 to the address of array in this step to compute the actual address of array b. And then we just load that into the register, and then we increment. So the answer is pretty similar to what we did. We do the exact same thing. We just find the bth element of array. We then add it together to compute the actual address, and then we load the register. However, the key difference I want to point out here is that for this load of x5, we use the immediate value 8. And the reason why we use the immediate value of 8 is because our array looks as follows. So you have an array with like maybe one element. Let's say we have an array of, I'll just write out the first 3 elements to make it a little easier. So we know that there's a real and an imaginary value in each part. And we know that for each index, the real is going to be bits 0 or bytes 0 through 7, while the imaginary is going to be bytes 8 through 16, as each index has a size of 16. And since we want the imaginary number in this case, we're going to use an immediate value of 8 to offset our address. Alright, next what we're going to cover is bit manipulation. So I know you guys covered this in discussion 1, but I think bit manipulation is very useful for the simulator to extract the opcodes and the registers and the offset fields. So we're just going to go over a quick review over bit manipulation. So the way we manipulate bits in C is through shifting. We have the left shift and the right shift, and I hope you all are very familiar with those. Basically, a single left shift is the equivalent of multiplying by 2, while a single right shift is the equivalent of dividing by 2. And then right here in the slides, it just goes through a quick example. Basically what it does is you have int a is equal to 18, and then when you shift it by 2, you're just doing 18 times 2 times 2, and that's equal to b. However, the important thing to note is that shifting a, just doing like something like a shifted by 2 to the left by 2, doesn't actually modify a. You need to reassign it if you want to modify it like it says here. Next, what we're going to do is we're going to cover some bit manipulation with the bitwise and operator. So the way the bitwise and operator works is it performs a logical AND between each of the two numbers. So from 203 or 270, you guys should be familiar with the AND operator in this truth table. Basically, if the 2 bits in the AND operator that are sent to the AND operator are zeros, if any of the bits sent to the AND operator are 0, it outputs 0, as you can see on the right. And then this is just a quick example of doing a logical AND operation. You can see that in the least significant bit, you have a 0 here, and you have a 1 here. So when you AND those together, you also end up with a 0. Why this AND operator might be useful is because you can use masking. You can use it for masking. So this lets you change all but some useful bits to 0. And as you can imagine, this can be very useful for extracting bits. Let's say you want to extract the opcode bits of the machine code you read in for the simulator part of the project. What you could do is you could come up with a mask that masks off the specific opcode bits, and then AND them together. Then you would get the specific opcode bits only. And then we have the bitwise OR operator. So the bitwise OR operator performs a logical OR between 2 numbers. So if either x is 0, or if either x or y is 1, that means it returns a 1, as you can see on the right. And then this, again, just walks through a quick example of using the logical OR value. And what's nice about the bitwise OR operator is you can set bits without changing any other values. So let's say we wanted to set these bits specifically to 1. We could just OR it with 1, 1, 1, 0, and all these bits would be set to 1, irregardless of what was previously there. And then this is just a quick example of kind of what I just said. So we want to set bits 7 through 4 of the given integer a to be 0b1011 without changing any of the other bits. So the way we can do this is first we come up with a temporary integer. So uint 32t. And then we just set it to be the bits we want. So we want bits 7 through 4 to be this. So what we're going to do is we're first going to initialize that to be 0b1011. Then what we're going to do is we're going to shift t to the right, or to the left by 4. And then we can just OR t with a. And then we set bits 7 through 4 to be 1, 0, 1, 1. And this is essentially kind of the same thing I just said. Next, we're going to come up with a mask to extract certain bits. So I'm not going to walk through it again, it's just in the slides. Essentially what's going on here is we come up with a temporary variable that's all 1s for the bits we want to extract. Next, we shift that left to get the 4th through 7th bits, so this is bits 4, this is bit 7, and we just use the logical, or the bitwise and operator, and then we just shift it down so we extract bits 7 through 4. One thing I want to note here is that the logical OR operator, it looks like this. It's 2 of the bitwise OR symbols next to each other. This is useful for like booleans or if statements, but you do not want to be using the bitwise and the bitwise OR operators in any if statements. Otherwise, you might have some unintended code. I hope this discussion was helpful, and if not, just post the questions you have on Piazza or come to office hours. Thank you.